So let's start with the plan of today. So we are going to consider percolation and ZD. And we are going to prove two things. So the first thing is that when P is smaller than PC, then the probability for 0 to be connected to the boundary of the box of size n decays exponentially. Okay, so there exists a constant that depends on P, which is positive, so that this holds. And the second thing is that for P larger than PC, we have that theta P is larger than P minus PC over P times 1 minus PC. So maybe let me comment about this lower bound. So theta P, remember it's the probability that 0 is connected to infinity. And what's significant in this bound is basically that, there's a color. Okay, so what's significant here is that you get that, okay, at the right neighborhood of PC, basically theta P increases at least linearly. So in general, we don't know much about what happens at PC, okay? But what we know is that at least, for instance, the first derivative of theta P is discontinuous. Okay? So this is the kind of lower bound it gives you. Okay, so this is P, this is theta P, and this is the kind of lower bound you have, okay? So this, okay. So this would be the kind of lower bound you have. But in general, you're not, yeah, it's not possible to prove that theta is not discontinuous. So in particular, I mean, nobody believes this, but you could have the green curve. Okay. Okay, so. So what are the tools we are going to use? So for the first inequality, we are going to use BK inequality. And what does BK inequality say? It says that under the percolation measure, the probability of A and B being disjointly satisfied is smaller than the probability of A times the probability of B. So I gave a proof of this yesterday. Maybe what I forgot to say is about the intuition of why this is true. But the idea is for this event to be satisfied, basically, well, first you need A to be satisfied, and then you need B to be satisfied, but you cannot use the edges that you have used for A. So in a sense, the open edges that you have used to satisfy A, they are considered closed for B. Okay, so B sees more closed edges than a regular environment, so this is the reason why, like, this is true. This is true. Okay, because once A is, okay, here A being satisfied doesn't help you because you're not allowed to use the edges, the open edges that you've seen to satisfy A. Okay, so this is where the intuition is, and this is not really clear how this intuition matches with the proof, but yeah, I think now there is no proof that kind of is really built on this intuition. Okay. And for the second part, we are going to use Rousseau's inequality, Rousseau's identity. Which says that the derivative of the probability of A is equal to the expectation of the number of pivotal edges for A. Okay, and if you remember the pivotal edges, there are these edges that, okay, I mean, roughly speaking, these edges for, if they are closed, A is not satisfied, and if they are open, A is satisfied. If you're allowed to look at everything without knowing the state of this edge. Okay, and here. Okay, and here I'm always considering increasing events that depend on finite lineages in these two cases. Okay, so okay, so what's the main idea of the proof here? The idea is that the proof of these two results is really coupled because, okay, what happens is that we are going to prove something like this, but for a value of P, which is not PC, but which is defined in another fashion, okay? And then we will see that actually okay, if this result is valid for some PC tilde, okay, then PC tilde must be equal to PC. But, okay, so, okay, let me introduce who PC tilde is. Let me show you what we are going to prove, and then we will see that readily this implies these two things. Okay, so so let me consider S a finite subset of ZD. Given S a finite subset of ZD, I'll define delta S to be the set of edges going out of S. So it's a set of X, Y in E, such that X in S and Y not in S. Okay, and basically, yeah, I don't know, I'm not sure, but I might use kind of improper notation during this lecture. When I write x, y in S, I will kind of always consider that x is the vertex which is in S and y which is the vertex which is not in S. Okay? I will always write the vertex which is in S first. And if 0 belongs to S, I define phi p of S, which is pi times p, times the sum over these edges in delta S of the probability that 0 is connected to X in S. Okay, so this means that there is an open path in S linking 0 to X. Here you see that we have a sum which is on the number of on the edges here, but that there is no dependence in Y here. What does it mean? It means that if you have X, which is here, okay, here is S, and imagine that you have Y and Y prime. Well, this X, it corresponds to two edges in delta S, so it appears, this term here would appear twice in the sum. Okay, just to say that there is no mistake in the fact that Y doesn't appear here in this expression. Okay, and what's phi ps in words? It's the expected number of open edges going out of S from a path connected to 0. Okay, so in a way it kind of measures the number of ways you can get out of, the expected number of ways you can get out of S if you want. Okay, and okay, because I mean basically this is okay. This is the same thing as the sum over xy in delta S of the probability that 0 is connected to X and xy is open. Okay? This event doesn't see the edges in delta S, so these two things are independent. So you just get a P out when you compute this probability. So phi ps is also equal to this. Okay. So now let me define some P tilde C, which is equal to the infimum of P such that, no, the supremum of the P such that the infimum of phi ps is smaller than 1. Okay, and an observation which will be kind of relevant for some other remark in the lesson is that actually this doesn't occur at p tilde c, because this thing it's a continuous function of p, for any fixed s. It's just a polynomial in p, because this is an event that depends on finitely many edges. So therefore, if for some value of p, this thing is smaller than 1, then for values that are just a bit bigger, it's still smaller than 1. So therefore, the set of edges such that the inf is smaller than 1, it's an open set. So therefore, it cannot contain its boundary. So what we are going to prove is that for p smaller than pc, the probability that 0 is connected to the boundary of the box of size n is smaller than exponential minus cpn, and for p larger than pc, theta p is larger than this. But the idea is that now if you look at these two things, they imply that PC is equal to PC, so this implies that one and two holds. This one prime, well, this implies in particular that this probability decays to 0. So this implies that if P is smaller than P tilde C, then P is smaller or equal to PC. So this implies that so this implies that P tilde C is smaller than PC, and this implies that P tilde C is larger than PC, because we know that if you're larger than this, then theta P is positive. So even though we are proving exactly the same thing, we prove it in a slightly different manner, because we are going to use this definition of PC. And somehow this definition of PC is kind of a byproduct of the result. So it's kind of intricate. And let me mention a consequence of this result. So what do we have? Yes. So So let me define, psi p being the expected number of, the expected number of vertices that are connected to 0. So the size of the percolation cluster that contains the origin. So what we have is that for P smaller than PC, well, okay, let me start for P larger than PC, what we have is that this thing is infinite with probability theta p, which is positive. Okay, so therefore the expectation is infinite. Okay, so not something very interesting here. For P smaller than PC, on the contrary, what you have is that, well, phi p, it's equal to, well, the sum over x in ZD of the probability that 0 is connected to x. Well, this is equal to, well, the sum over n larger than, well, okay, it's 1 plus the sum over n larger than 1 of the sum over x, which have infinite norm, okay, n of the probability that 0 is connected to x. I'm just reorganizing the sum. And now this thing, it is smaller than the probability that 0 is connected to the boundary of n. Okay? Because this guy belongs to the boundary. Okay, so that in particular, this is smaller than exponential Cp times n. Okay, so what we get out of this is that this sum is smaller than 1 plus the sum over n larger than 1 of, okay, the cardinality of this times exponential minus Cpn. This belongs like n to the power d minus 1. So, and this is exponential. So the sum is finite. Okay, so phi p is infinite in the supercritical regime, which is not surprising and for which we have not used the result. On the other hand, the expected size of the cluster containing 0 is finite in the subcritical regime. And the last thing we have is that for P equal to PC, this remark here allows us to show that, well, we don't know if theta p is positive. We actually suspect that it's equal to 0. But so what should happen for P equal PC? So we call that we believe that theta PC is equal to 0. So what will happen is that, okay, we believe that the cluster is almost surely finite, but actually its size has infinite expectation. And how do you prove this? Well, if you look at the sum over x in ZT of the probability that 0 is connected to x, well, this is small. This is larger than the sum over n larger than 1 of the probability that 0 is connected to the boundary of lambda n. Okay, so why is this true? Well, it's simply because if you look at this, this thing, it's the probability that there exists an x on the boundary which is connected to 0. Okay, so this is smaller than this. Okay, just by the union bound. Okay, so using this inequality and decomposing ZD into these kind of shells, and okay, I can put 1 plus here, but it's not really relevant. I can just forget about the fact that the origin is always connected to the origin. Or maybe, wait. Yes, I erased the definition of phi p, and maybe I shouldn't have. Maybe this is not what I wanted to write. Let's see. Yes, okay, so this is true, but this is not really relevant, so I'm sorry about this. Okay, so what I want to say is that this is larger than 1 over p sum over n larger than 1 of phi lambda n. Okay, and maybe I need a constant. Okay, so let's look at what phi lambda n is. Okay, so phi lambda n, it's the sum over xy in delta lambda n of the probability that 0 is connected to x, and times p. Okay, so this is smaller than 1 over d times the sum over x in lambda n times the probability that 0 is connected to x in lambda n. Okay, and this is smaller than p over d times the sum over lambda n times the probability that 0 is connected to x. Okay, so I think here I should have maybe no, it's a d. So d here. Here I have 1 over dp. Okay. Basically, what I want to say is that I want to compare this. Okay, I want to compare this with this sum, and if I get this sum, then I'm done, because this is really this sum here is really the sum over n of this. Okay, and basically the only difference I have is here I have this prefactor p. Okay, so you have to get this 1 over p here. And here, I'm not counting the edges on the boundary, the vertices on the boundary. I might count them more than once. Okay? just because there might be as many as d outgoing edges from the boundary. Okay, so for instance, in the corner of your cube, you have d outgoing edges. Okay, so even though for most x's you have only one edge, I'm just going to overcount and assume that I have d possibility for y for every vertex. So this gives me this inequality. Okay, and this gives me this factor. Okay, now I know that, okay, sorry. This is larger than 1 for p equal pc, which is equal to pc. So therefore, this is equal to infinity. Okay, so in any dimension, okay, what you get is that at criticality, the expected size of the cluster containing 0 is infinite. So the idea is that, yes, you have really, you have a supercritical regime and a subcritical regime that are different, and at criticality, you observed a third behavior, which is kind of in between. Okay, and a milder consequence of this, okay, is that at criticality, you don't have exponential decay of correlation. Okay, so this thing is clearly not true for P equal to PC. Okay, so any questions so far on the results and on the consequences that I have discussed? Okay, so let's try with the proof. Let's start with the proof of exponential decay. So first thing we are going to do is use our assumption. So given P smaller than PC, we fix S such that phi PS is smaller than 1. Okay, the infimum is smaller than 1, so we can find some S. And then what we can do is we are going to prove that, so we fix L such that S is included in gamma L minus 1. Okay, so the idea is that we want S and the outgoing edges to be included in lambda L. So this is really lambda. I don't know. Maybe I'm saying gamma half of the time, but this is lambda. And what we are going to prove is the following. So we are going to prove that for every k larger than 1, the probability that 0 is connected to lambda to the boundary of lambda KL, it is smaller than exponential. I'm just checking that I am using the same letters in my notes. Yes. It's not exponential, it's phi ps to the k. Okay, so from this it's not too difficult to see that this implies what we want to prove, but okay, let me do it for the sake of completeness. So okay, let me define C1 of P, which is 1 over 2L log 1 over phi ps, and C2 of P, which is the minimum of 1 n minus 1, 1 over n log 1 over p, p 0 connected to lambda n. Okay, so, and let me write Cp, which is equal to mean of C1 of P, C2 of P. Okay, so then what you observe is that, well, by definition, if n is smaller than n minus 1, then the probability that 0 is connected to lambda n, it is smaller than exponential minus n C1 of P. Okay, so for n equals 0, it's kind of obvious. And for L between 1 and n minus 1, I think this just comes from this definition. So let me check that I have not written anything stupid. Yes, this is true. Okay, and here, okay, C2. Okay, this is defined as the minimum. So this just gives you this inequality for free. Okay, and the fact that for any n, okay, this is always smaller than 1, this gives you that C2p is positive. Okay. Now, if n is larger than L, what we have is then the probability from 0 to lambda n is smaller than exponential minus n C1p. Okay, so why is this true? Well, it comes from two things. So basically, this thing is decreasing in n. So you can always take, this is smaller than, well, instead of taking n here, you can take the largest multiple of k that is smaller than n. Okay? And this large, okay, and for this multiple of k, basically this thing would be true with with not C1, but with 1 over n log 1 over phi ps, okay, just because of this. Okay, here I've taken a factor 2, because basically the largest multiple of k, which is smaller than n, it can be, the largest multiple of L. Largest multiple of L. Okay, because here I have already exponential decay for multiples of L, so I'm just trying to fill the gaps. Okay, so this is decreasing in n, so this is smaller than 0 delta maybe L times the integer part of n over L. Okay, and this is smaller than phi p s times n over L, and now the idea is that this is smaller than phi p s n over 2L. Okay, I'm just using the fact that this is larger than the half, and it's just because n over L is larger than 1. Okay, so so this is the, okay, I've done this in this particular case, but what you can say for sure in the future is that if you have a sequence which is decreasing in n and which is, well, smaller than 1, okay, and if you know that it decreases exponentially along a subsequence which is dense, which is a subsequence which has positive density, then you know that it decreases exponentially. Okay, this is just what I've done in detail, but it's possible that in the future people don't explain you why this implies that you have why this implies this inequality for every n. Okay, so what we are going to do is to prove this by recursion on K. Okay, so maybe the first thing we could do is prove it for K equal to 1. And then, yeah, maybe a remark. You see that CP is not very explicit because I don't know very much about this S, so I don't know a lot about this. So just to say that this is something kind of abstract, and you need something more if you want to have some estimates on this. Okay, so I guess. Okay, so the idea is that so if 0 is connected to the boundary of the box, what happens is that if I follow a path connected to zero, from 0 to the boundary of the box, an open path, well, there will be a first time at which it exits the set S. Okay, and when it exits the set S, basically, well, it will use an edge in delta S, okay, which will be open. Okay, and well, the path linking the first vertex in this edge to 0 will also be open. Okay, so this is smaller than the probability that there exist xy in delta S such that 0 is connected to x in S and xy is open. Okay, now as soon as I have this quantificator, this means that I have a union of events. And if I have a union of events, I can bound the probability by the sum. So this is smaller than the sum over xy in delta S. So here what's really important is that, yes, all the vertices that involve edges in delta S are in gamma L, lambda L. So this is why it's important. So this means that if E in delta S, E is included in gamma L. This is what I'm using here. Okay, and then if I look at the probability of this, okay, so let me write this. The probability is that 0, x, and xy is open. Well, now by independence, I can just multiply the probability, and the probability of this edge being open is just P. Okay, so this thing is just equal to 5 pi of S. Okay, so this is, we have proved the initialization of our induction. Now we can do the induction step, and it's not much more complicated. So now let us look at the probability that 0 is connected to delta L k plus 1. Okay, so we are going to do the same reasoning, except that now we are going to also care about this second pass. Okay, because here we have basically thrown away this. Well, maybe, okay, well, you deep one. Okay, I will just, sorry, just keep this. Just erase this. Okay, so okay, so I mean, just imagine that the box is much larger now, or that S is much smaller. But the idea is kind of the same. So if 0 is in, so then you have three things that happens. First, 0 is connected to X. Then X is connected to Y. And then Y is connected to the boundary. The thing is that this path, which is linking 0 to the boundary, I can choose it to be self-avoiding. Okay? I just take a path that connects 0 to the boundary, and if it's necessary, I just erase the loop that I'm forming when I follow this path. Okay, so this means that this thing and this thing, they are S-disjoint. And also, they do not contain that edge. So, you know, these three events, like 0 is connected to X in S, Y is connected to the boundary, and it's really Y is connected to the boundary. It's not Y is connected to the boundary in the complement of S, okay, because it can visit S back. Okay, so this is important. But it's Y is connected to the boundary disjointly from the fact that 0 is connected to X. Okay, so if you want, this thing, it is smaller, or it's actually equal, yeah, it's actually equal to the probability of the union over xy in delta S, okay, that 0 is connected X, xy is open, and y is connected to lambda. Okay, so what I get here is that P that 0 is connected to delta L lambda gamma L k plus 1. This is smaller than the sum over x, y in delta S, probability of 0 S x, xy is open, y lambda. Okay, so here I need to make a digression, I guess. Oh, yes, and I can, yes. So far, last time I just defined A circle B, and now I'm writing A circle B circle C. So, okay, so you remember that if A and B are increasing, what we have is that A circle B is increasing. Okay, this is something that I left as an exercise. Okay, so we can always define this thing. Okay, and what you can check, so this is an exercise. So that this operation circle is associative. Okay, and if I write this without parentheses, the natural definition that I would give to this would be there exists YA, YB, YC disjoint such that A satisfies IA satisfies A, IB satisfies B, and IC satisfies C. Okay, so the fact that this is true is quite natural. Maybe it's better to check it to make sure. Okay, because of this, basically, you can just iterate BK inequality to see that it's valid for 3 events instead of 2. Okay, and it's also valid for K events instead of 2. Okay, just by induction. Okay? Okay. Using the fact that this is equal to this, I have this, and then I just apply BK once more to have this. Okay, so I don't really need that here because I could just apply BK to these 2 events and just say that this thing is independent. But I don't know, I think it's something interesting in itself. So. Okay, so now I'm going to apply BK. So this is smaller than P times the sum over xy in delta S PP 0 S X. And then I have PP Y. Okay, and here it's not L, N, it's K plus 1 times L. Okay. Now the idea is that y is at most at distance L from the origin. Okay, just because of the thing I just erased. Okay, S is included in lambda L minus 1. Y is at distance 1 from S at most. So it's distant from the origin is at most L. So this thing, it's included in, okay, and this, okay, I'm sorry, I'm kind of messing up all the notations here. This thing is included in the event Y is connected to this. Okay? If it has a connection, it has a connection to this box. This box, any point of this boundary, it's at least at distance KL from Y. Okay, because it's at distance K plus 1 L from the origin, and Y is at distance smaller than L from the origin. Okay, now by translation invariant, this has the same probability as 0 is connected to. And there are 2 kinds of blue chokes. Okay, so this is really good. So here I have something that depends on Y, but I can bound it by the probability of something that does not depend on Y. So I just put this probability into factor, and I get that this is smaller than P times the probability that 0 is connected to delta KL times this thing. And this thing is just phi ps. And I have no p here because the p is here. Okay, and this is just what we need for the induction step. Okay, we see that going from k plus 1, okay, now we can use the induction step basically to say that this is smaller than phi ps to the k. Okay, and this is where we get that, the k plus 1. Okay, so now what we have seen the proof, the intuition of why this works is quite clear. Okay, basically, to go outside of this box, you kind of need to go iteratively k times out of S. Okay, just go once out of S, and then you have to do it again, but in a disjoint manner. Okay, so using this BK, in fact, I mean, we could have done it without the induction if you want, just using this kind of sausage and using a BK with a lot more events. Okay, and yeah, basically each time you want to get out of S, well, the probability of doing this is smaller than phi ps just by this union bound. Okay, so now we can go through the proof of 2 prime. Okay, which at least to me it's a bit more mysterious why this works, but it's based on Rousseau formula. And okay, the idea is that if phi p of S is not small, okay, if phi p of S is not small, even for large boxes, basically this gives you a lower bound on the expected number of pivotal edges. For the connection events. And this allows you to get a bound for the derivative in P of the probability of being connected. Then you integrate this bound, and this gives you a bound on theta P. Okay, so let's see how this works in practice. So any question about this the proof of 1 or of 1 prime? So let me write theta np, which is equal to pp of 0 connected to the boundary of gamma n, of lambda n. Okay, and what we are going to prove is the following, is that the derivative of theta np is larger than 1 over p1 minus p times the infimum of S included in gamma n, such that 0 belongs to S of phi ps times 1 minus theta n p. Okay, so for every p in 0, 1. Okay, so this is what we need to prove. And let me first show you why this implies the desired lower bound on theta p. And the idea is just to integrate out this. So how does this go? Well, okay, so what we, okay, this inf, okay, so if P is larger or equal than PC, this thing is larger than 1 by definition. Therefore, what we have is that delta P of theta np over 1 minus theta np, it's equal to 1 over P 1 minus P. Okay, and this is equal to 1 over P plus 1 over 1 minus P. Okay, so now these two things are derivatives of logs. So, okay, I mean, this thing, integrating out this, it's not very difficult. I'm just making the details because I think, okay, to encourage you when you encounter something in lecture notes, when they say, okay, just do this, it's important to make the details to make sure that everything is all right. So this is the derivative of log 1 over 1 minus theta np. And the other thing is the derivative of, well, log p minus log 1 minus p. Okay, you have a minus because, okay, this is the derivative of, yeah, this is not the derivative of log 1 minus p because you have this minus that appears when you do the composition. So this is the derivative exactly of this function. Okay, so now we can integrate this between 0, we integrate this between, okay, so for P larger than PC, we integrate on PC P. And what we get is that log 1 minus, okay, let me just write it like this. Theta np minus log 1 minus theta npc is larger than log p over 1 minus p minus log pc 1 minus pc. Okay, so now what can I say? This is smaller than 1, right? So this means that this is larger than 1. So this log is positive. Okay, so this means that this inequality is still valid without that. Okay, and the reason why there is no big harm in deleting this is, I mean, we expect this to be equal to 0 anyway, when to tend to 0 when n goes to infinity. So taking this away should not be a big deal. Okay. And from this, what we get is that 1 over 1 minus theta MEP is larger than P1 minus PC over 1 minus P times PC. Okay, I'm just taking the log of the quotient here, and then I'm taking the exponential of my. Okay, and now you can conclude from this, then this thing holds. P1 minus PC. Okay. Just invert, I mean, take the inverse and reverse the inequality and then put the one on the other side. From there, it's not hard to conclude. Okay, why exactly this is true might not be obvious from there. Okay, so okay, this is true, and then you make n tend to infinity, and you get this. Okay, or if you prefer, you get that theta p is larger than this. No, theta p is actually smaller than this, yes. So you just take n to infinity. And because this does not depend on n, you can conclude. So, yes, so, okay. Unless you're really good in computation, it's not completely obvious how this gets you this in the end, okay, even when you've taken this away. What is actually not difficult to see is that this will give you, you know, the fact that theta p grows linearly. Okay, why? Well, in the way that you integrate, this is going to be bounded away from 1. This is going to be always larger than 1/4. Okay, and this is larger than 1. So if instead of this you just want theta in P is larger than P minus PC over 4, okay. It's maybe over 8. Yeah, on the neighborhood of PC, well, yeah, just say, okay. Yes, it's a bit, yeah. Okay, so. Yeah, it's a bit annoying. I mean, first you have to assume that if you want to show that you grow linearly, then you grow at least linearly. Well, you can assume that theta of P tilde C is equal to 0, because if not, you would have nothing to prove. Okay, and once from continuity, you can basically replace that by 1/2 if you take P small enough, and then you can integrate. Okay, just to say that this kind of intuitively gives you the fact that you grow at least linearly. Okay, just because this thing is at least 1/4, and if you want to prove that you grow linearly, this thing is close to 1. Okay, so I guess we just have to prove this lemma and we will be done. So let's see how this works. Okay, so okay, let me just write. Okay, maybe I will not even use this, but so, okay. So in the proof, what I'm going to do is that when I write E is pivotal, it means E pivotal for AN. Okay, because this is pretty much the only event that we are going to consider. Okay, so what we are going to use is Rousseau's formula, because so this is what we are trying to estimate, and we know that it is just the expected number of pivotal edges, so it's the sum over edges in lambda n of the probability that E is pivotal. Okay, so now I have to somehow introduce this set S. So, okay, basically, what S is going to be, so I'm going to introduce a random set, okay, which is going to be the set of x's in lambda n, such that x is not connected to the boundary of lambda n. Okay. I mean, basically, it's kind of, you want this set to contain 0. Okay, if this set is going to be related to this, it's better than 0 is in there. So for 0 to be contained in this set, you want to make sure that AN is not satisfied. Okay, you want to make 0 not. So I want here E to be pivotal and closed. Okay, so this event here, it's included in A and C. Okay, by definition, if an edge is pivotal, when it's closed, then the event does not hold. Okay. So now this event here well, it's the union over S in lambda n, 0 contains S, of E pivotal, E closed, and S equal S. Okay, I can sum over these things because I know from the fact that AN is not satisfied that 0 has to belong to this random S. Okay, so when I take the realization of S here, I can just assume that 0 is in it. Okay, so now if I use a union bound, okay, I will get 1 minus P sum over E in lambda n. And okay, I have to check that I'm not making a mistake. Yes. So sum over S in lambda n, E S 0 in S. Yes, okay. So this is, well, this might seem kind of worrying, but the fact that you have a sum and here you have an inf, but the idea is that inside the probability, then we will have something that that tends to 1. Okay, so E pivotal and closed. And S equal S. Okay. So, okay, let me triple check this. Okay, so let me make a picture. So this is S, this is lambda n. Okay. And this is 0. Okay. So now I know that basically, okay. Okay, and S is not necessarily connected, okay, but the only important thing here is really the connected component that is going to 0. So because E is pivotal, okay, so basically we know that all the edges going out of S, they are closed. And we know that all the vertices outside of S, they are connected to the boundary. Okay, by definition. Vertices outside of S, they are connected to the boundary. And these edges in delta S, they have to be closed because if not, this thing would be connected to the boundary, and this thing is in S, and things in S are not connected to the boundary. Okay. So now I want to know what could be a pivotal edges for the event that 0 is connected to the boundary. And the thing is that if I want to connect 0 to the boundary, the least I have to do is to open an edge in delta S. Okay, so I'm sure that if I open an edge inside of S, it's not going to make any difference. Okay? And also, if I open an edge which is with both ends outside of S, it's not going to make a difference either. So this sum here I can somehow make it a sum over E in delta S. Okay, just because this event has probability 0, okay, if E is not in delta S, because it's an empty event. Okay. Okay, and now let me call xy this edge. And if I call xy this edge, the event that E is pivotal and closed, and S is equal to S, this is basically the event that 0 is connected to X, E is closed and S is equal to S. Okay, so write this. If xy belongs, or if E equal xy belongs to delta S, what we have is that E is pivotal and closed. And S is equal to S. This thing is equal to 0 is connected to X in S. Okay, XY closed and S equal S. Okay? So from all of this, I get that this derivative that I want to estimate, this is smaller than 1 over 1 minus p times the sum over S, the sum over E in delta S, okay, xy, in delta S times the probability that 0 is connected to S in X, xy is closed, and S is equal to S. Okay, and now I'm having some little doubt. Oh, yes. Okay. Yeah, so this is true, but actually, I don't really need this. Right? Because if S is equal to S, this implies that this edge is closed. Okay? Because if not, then X would be connected to the boundary of the box, and this would give me a contradiction. Okay, so it looks like we are almost done, and we just need an observation to conclude, and the observation is that these two events here, they are independent. Okay, so why is it so? Well, I just need to rewrite the event S is equal to S. I'll do this here. So I will just rewrite this event in order to make it explicit that it only depends on edges that are outside of S. So either in delta S or with both vertices outside of S. Okay, so this event, I can rewrite it as follows. So for all xy in delta S, xy is okay. For all E in delta S, E is closed. And for all Y in lambda n minus S, Y is connected to the boundary of the box using paths entirely in the complement. Okay, and you can see that, well, this first thing does not involve anything in S, okay, because these are the boundary edges. And the second thing, it involves only the edges that are on the complement. Okay, so I don't need to look at any edges in S to know that this is true. Okay, and you can check that this really corresponds to this. Okay, I mean, basically, what I'm checking is not that S is a set of vertices that are not connected to the boundary, but rather than the complement of S is a set of vertices that are connected to the boundary. Okay, so this depends on edges that have both, that have at least one edge, one end outside of S. This depends only on edges that have both ends inside S, so these two things are independent. Therefore, what we get is that this is equal to 1 over 1 minus P sum over S P S equal S times the sum over X, Y in delta S. And then I have 0 X in S. Okay. Now this thing is exactly phi p of S, except for a factor p here. Okay, it's exactly phi p of S over p. And in particular, what I can say is that this here is smaller than the infimum of the phi p of S prime, okay, over S prime in this set, clearly, because the sum is. And now I guess I just have this sum, but this sum is equal to 1. Okay, so 1 over p, 1 minus p, times this infimum over S prime, and now I have the sum over S. Okay, and this sum is equal to 1. Okay, and then we have proved exactly what we wanted to prove. Okay, and I think pretty much all I had done until now, it was present in all the reference I had given. Now this proof is quite recent. So you can find it in 2 versions. So the original is a paper of vinyle, copain et notation. I think it's 2015 or 16. Okay, and it's, if you put these two names and you look at exponential decay, then you will get the paper. You will also find it in Grimet lecture notes, but you have to make sure that you look at the last version, which is from so I think it's probability on graph. Okay, you can find it on Grimet's web page, so Geoffrey Grimet from Cambridge. And this is a version from 2018. Okay, and basically before that, yeah, there was a proof of exponential decay that was relying also on Rousseau and Decay, but it was much more complicated. Well, you can see it in the other references if you want, but okay, all of that I've shown you today, I mean, it looks quite simple, but it basically took 30 years to get this simple proof. So, like, don't be worried if you think, oh, this looks really smart. How could these people have this idea? Well, it's several people thinking for 30 years, and only a couple of them getting the idea. So. Okay, so and maybe I can give you a last conclusion about. A last comment about this bound on theta p. So basically, what I told you is that what was important was that important from this was that what you get from this is that theta p is larger than some constant times p minus pc plus on a neighborhood of D. Of PC. Okay, so one thing that what might wonder is this thing sharp in any way? So in terms of the constant, I think it's really difficult to. Yeah, you're losing you're losing something when you do the inequality, basically, when you're doing these union bounds, because yeah, basically, yeah, you're doing union bounds where the events are not disjoint, and most of the time, yeah, in this union, two of the events could happen. I mean, a finite number of these events could happen. So you're losing a bit, but maybe you lose only on the constant. And it turned out that this is actually sharp for D large. Okay, so I think D larger than 11. Okay, just to be checked. So okay, this is small CD and this is large CD. So basically, you can find a large constant such that theta p is smaller than p minus pc plus. Okay, and this is quite complicated to prove, but the overall idea is that when the dimension is large, basically, the percolation clusters at criticality should be kind of tree-like. Okay, it's difficult to make. Okay, if you know something about the random walk, it's recurrent in dimension 1 and 2, but in dimension 3 it starts to be transient. And if you look at it in dimension larger than 4, so 5 and more, if you look at it from far away, it won't make large loops. Okay, so in dimension basically larger than 5, random walks, they look like self-avoiding paths. Okay, the idea here is that when dimension is larger than 7, okay, percolation clusters at criticality, they kind of look like tree. They are not, the graph is, the dimension is sufficiently high so that it's difficult to make cycles. Okay, and basically because of this, the idea is that the phase transition should be really similar to the phase transition of the percolation on trees. Okay? The idea is that microscopically, okay, you may have some small cycles, but on the large scale, things behave tree-like, and large scales are basically what matters. So I'm a bit hand-waving, but it's just to underline the fact that there is one case where we have the expression of theta p, or we have computed it. Okay, it was kind of an implicit expression, but so for phi d, okay, the d plus 1 regular tree, if you remember, and if you have done your homework, what we have is that theta p is equal to p minus 1 over d. Let me see, I have written the expression. I think it's d3 over d squared minus 1. Plus little o of p minus 1 over d. Okay, so basically, on a tree, theta p really behaves like p minus pc at the neighborhood of the critical point. And it's kind of, you can now check that this constant you get here is basically not the one you get from this constant you get here is not the one you get from this proof. Okay, this proof, we made the proof on ZD, but everything works also on trees. But even on trees, it's not sharp. Okay, I think the constant you get would be d squared over d minus 1. So kind of asymptotically the same when d gets large, but not quite. Okay. So this is from today's proof, and this is what you get from the. And what's kind of reassuring is that this is smaller than this, so there is no contradiction. Or is it? Okay. Okay. You can compute the constant, and maybe it should be smaller than this. Okay. Any questions? Okay, so what we are going to do tomorrow, and I think this will kind of close what we will do on percolation, okay, at least in this setup. Will be to look specifically at Z2. And try to see, I mean, basically, things that are very specific to dimension. So we have seen that if you try to cross a square, okay, a square that was just a tiny bit rectangular, like it was a square which was, I think, 2n by 2n minus 1, but let's say that was seen from very far away, it's a square when n is large. We have seen that the probability at criticality to cross a square is 1/2. Okay, so now the question is, what's the probability to cross a rectangle? Basically, if you know this, can you say that the probability to cross this is, yeah, like bounded away from 0, uniformly in n? Okay, if you take a rectangle which is, say, n by 2n, and you want to cross it in the hard part, okay, so this, I mean, this is more difficult to cross than this, okay? So can you bound it away from 0? And part of the answer is, well, basically, if I want to cross a rectangle of ratio 2, it's sufficient to I have n, now you have 3n over 2 here. And the idea is that if I cross this rectangle, and this square from top to bottom, then I'm crossing the larger rectangle. Okay, so if I want to show that I cross this rectangle with a positive probability which is bounded away from 0, it's kind of sufficient to show that I'm crossing rectangles of width 3 half over n with probability bounded away from 0. Okay, and basically extending this argument, if I can show that I can cross this rectangle with a probability that does not decay to 0, then I'm kind of done, because I can basically repeat this argument to go up to 3n over 2 and then to 2n. Okay, so, but I only know things for square. So what we are going to see tomorrow is how you go from a square to this, and what kind of consequences it has on well, the connectivity properties at criticality. Any questions? Okay, so see you not tomorrow, but see you on Friday.